Hey everybody, welcome to the shop. I'm Gerald for Gerald Education. Now, today I'm going to be covering projectile motion. We're going to be doing a projectile motion problem on level ground. I'm going to use the acceleration due to gravity to be 10 because that makes it a lot easier to discuss and get numbers and stuff, but the same principles apply if you use some other acceleration, 9.8 typically here for Earth. But the way I'm going to structure this is I'm going to solve 3 different problems before we do the projectile motion problem. Okay, so the first one is just going to be shooting an object straight up into the air. All right. The second one is going to be looking at an object with constant velocity and just making sure you can do both of those problems. The third one is going to be a really simple triangle problem just from right triangle trig. And then you're going to see how we put those 3 concepts together and we're able to do a projectile motion problem with relative ease, I think. All right. You let me know what you think. Now, if this helps you and you like the content, please like and subscribe to the channel because it does help me out, makes me know that I'm doing the right thing, and I can make more videos. All right, so here we go. Let's get into it. All right, prerequisite problem number 1. We can solve this problem by using simply equations as well without drawing any graphs. So if I look at this, I could say, okay, I want to know when does it get to the top. But what do I know about that? Well, I know at the top the velocity is going to be equal to 0. So v is equal to at plus v sub o is one of our equations. Another equation that we have is the displacement, I'll call it delta y in this case, is equal to 1/2 at squared plus v sub o times t. All right, now, when it's at the top, I know that the velocity is equal to 0. So what I can do first is I can take this equation and I can say 0, the velocity at the top, is equal to -10, which is the acceleration, at what time, plus the initial velocity of 50, and I can solve this. That gives me 10t is equal to 50, which means t would be 5. So it's going to take me 5 seconds to get to the top, and it would make sense, since it's coming back to the same ground, it's going to take 5 more seconds to get down. So the total time it's going to take here is going to be t is equal to 10 seconds. Okay, so that answers the first part. Now if I look at this expression, now that I know the time, I can say, and remember, this is the total time, but this is the time it takes to get to the top, which is what I'm looking for. So I can say this, I can say delta y, or according to the picture, delta y is h, and that's going to be equal to 1/2 times -10 times 5 squared plus 50 times 5. Now this is equal to -5 times 25 plus 250. This is equal to -125 plus 250, which is equal to 120. Let me fix my 2 there. I got a problem writing 2's. 125 meters. So what we know, it's going to be in the air for a total of 10 seconds, and it's going to take 125 meters. That's how high it's going to go. Now we can do this problem simply by making a velocity graph and looking at all the parts. And if you've watched my older videos on this, you'll know this is sort of my preferred method. Okay, so here we go. If I draw a velocity graph, so this is v, this is t. Let me make this go down farther. Now the initial velocity is 50. The slope is -10, and I know it's linear, so I don't really have to think too hard about the equation being v is equal to -10t plus 50. The fact that the acceleration is constant means the velocity graph has a constant slope of -10. And since the slope is -10, it's very easy to figure out that that's 5. So because down 50 and over 5 has a slope of -50 over 5, which is -10. You could also set velocity equal to 0 and solve for t. But in any case, the total time, I simply just have to double this since it's coming back to the same ground, will be 10 seconds. So I know it's 10 seconds in total time in the air. Now the area under the velocity graph is equal to the displacement. In this case, that's h. So that's easy enough to find because if you look, this is just a triangle where the base is 5 and the height is 50. So 1/2 the base times the height is going to give me 50 times 5 is 250 times 1/2 is going to be 125. So I can find all my information that way as well. Okay, here's problem number 2 in our prerequisite problems before we actually get to the projectile problem. I have a particle. It's moving along the x-axis with a constant velocity of 86.6 meters per second. How far will this particle move in 10 seconds? Well, I'm going to start with my favorite way, and I'm going to draw a velocity graph. Okay, and I want you to note the velocity graph doesn't have to be anything beautiful. It's just a sketch. And if the velocity is 86.6, right, that means it's constant 86.6, and it happens for 10 seconds. Now the area underneath that, which is really just a rectangle, is equal to the displacement, and that's going to be 86.6 times 10, which is 866 meters. Okay? Now I guess I could even do this. I could say displacement. We know the equation, right? It's 1/2 at squared plus v sub o times t, right? But since the acceleration is 0 in this case, that goes away, and I'm just left with delta x is equal to v sub o times t, which is exactly what I did there on the velocity graph. So it's just 86.6 times 10, which is 866 meters. Same thing. Okay, here's the last prerequisite problem that we have to be okay with before we get into our projectile motion problem. I have to break this vector up into its x component and its y component. So, here we go. Now, first off, all you have to do is make this into a right triangle, just like that. All right, now the way it actually goes is this is the x component right here, and usually we write the y component right over there. But essentially, that's going to be the same length as that line right there. So let's calculate this. Now, if you're familiar with this, skip the section, move on. If you're not, check it out. I'm going to call this x, and I'm going to call this y. Now, using SOHCAHTOA, not getting into any crazy pre-calculus or anything like that, but I can say this, that cosine of 30, if I'm looking at this triangle right here, right? Cosine of 30 is equal to the adjacent side, which is x, over the hypotenuse, which is 100. And if I leave that and I cross multiply, I get x is equal to 100 times the cosine of 30. By the same argument with y, I can say sine of 30 is equal to y over 100 because it's opposite over hypotenuse. And then if I cross multiply, I get y is equal to 100 times the sine of 30. Now for x, 100 times the cosine of 30, make sure your calculator's set in degrees and check my calculations. But if I do 100 cosine 30, I'm going to get 86.6. And if I do 100 sine 30, I'm going to get 50. Now, you should be thinking right now, there should be a little aha moment going on in your brain. Wait a second, that guy just talked about something being 50 and something else being 86.6. Well, I need you to do that because now we're going to do the projectile motion problem, and knowing this is going to make that really easy. Hopefully. You're about to see an animation of a projectile flying through the air. Now, what I want you to focus on is the vertical and the horizontal components of the velocity and also of the displacements. We just got finished doing 3 problems separately. We did a vertical problem where the initial velocity was 50, and we looked how far it went up and how far it came down. And we also did a problem where the velocity was constant at 86.6. Now think of that as we go through. To solve a projectile problem, you're looking at the vertical and horizontal components separately, but you already know how to do this. The only difference is now we're combining vertical and horizontal into one problem. Okay, now we're finally ready to start actually solving the problem that we intended on in the first place. So here it goes. A projectile is launched with an initial velocity of 100 meters per second. So I know that. And it's 30 degrees to the horizontal. So there we are. Okay. Now you just watched the animation, and now this is right at the beginning of the cycle. So the first thing we have to do is we have to break up this vector. But I didn't waste our time when we did this earlier. This part right here, we've already done it. Here's our 100, our vector that was 100 at an angle of 30. Now, in this case, it's 100 meters per second, but that doesn't matter. It's just the amount of. And we figured out when we did this that the y component, we figured out that that was 50. That was right here. And the x component, that was 86.6. So rather than reinvent the wheel, if you need to see that again, just go back and watch that section. But here's what I know. I know that the vertical component of the velocity is 50 meters per second. And I know the horizontal component is 86.6 meters per second. Okay. So that means if this is vertical velocity and this is horizontal velocity, this starts out as 50. and this starts out as 86.6. Now the difference is this one changes, this one doesn't, because in the horizontal direction, there's no reason for the velocity to change. So again, all we're going to do now is to solve this problem. We've already done it. We already know what we're going to pretend is that this particle, yes, I understand that it's moving along that arc, but we're just going to look at it separately. We're going to look at its up and down motion, and we're going to look at its back and forth motion. But the good news is we've done it. Let me scroll back. In the up and down direction, if a particle is launched off vertically with an initial velocity of 50, we already figured out that it goes 125 meters and it takes 10 seconds to get back to the ground. So we don't need to do all that over again. We can go back here and say, okay, I know this is 5, I know that's 10, and I know that's 125. So that piece of the problem's already done. 125, finished. Now, as far as the horizontal range goes, we've already done that too. When we scroll back here and remember what this was, if something's moving with a constant speed in the horizontal direction, say of 86.6, and the speed's not changing, the distance that it travels is going to be 866 because it winds up just being 86.6 times 10, the area under that graph. Okay, and let me scroll back to our problem. That means in this direction, we're going to go, it's the same thing. This is going to take 10 seconds. This is 86.6, so it's going to be 866. So the whole point of this, all right, is when you're analyzing a projectile motion problem, it is the same thing as you did when you just did motion in one dimension with gravity problems and those kinds of things. The only difference is now you're adding in the horizontal part, but that is just looked at separately. And typically, especially in like your first physics class, the horizontal velocity is constant because there's going to be no forces acting in the horizontal direction. So to answer this question, finally, the two answers just to make sure that we have it. It's going to go a distance of 125 meters up, and it's going to take 5 seconds like we shown in the graph. And horizontally, it's going to go 866 meters, and it's going to take 10 seconds.